Welcome to part 3 of lecture 2 and chapter 13. We're going to back up a slide or two as we begin here from where we left off at the end of part 2. Here is a radical substitution of an allylic hydrogen. If a radical abstracts a hydrogen from an allylic carbon, the unpaired electron of the allylic radical is shared by two carbons. Of course, here we've got the two resonance contributors that share the unpaired electron. So the allylic radical has two resonance contributors. Only one substitution product is formed because the groups attached to the sp2 carbons are the same in both resonance contributors, as you'll notice here. So the source of molecular bromine that's noted here on the slide could have come from the N-bromo-6-cinnamide reacting with HBr in the previous slide that you saw earlier. Okay, let's go to the next slide. Unlike the previous slide, in this reaction, the groups attached to the two sp2 carbons of the allylic radical are not the same in both resonance contributors. So two substitution products are formed, as you can see. And it looks like both of them are correctly written on the slide. So let's go to the next slide. Now here's a question. Give the number of allylic substituted bromoalkenes that are formed from the reaction of 2-pentene with NBS. And we can ignore all the stereoisomers. Well, looking at this, here is our allylic carbons. We've got a primary over here. We have a secondary right here in 2-pentene. And we've got NBS and peroxide, so we're going to get bromine radical removing a proton from the 2-pentene. Now it's easier to remove a secondary hydrogen than a primary hydrogen. So we're going to get resonance contributors, as noted here, and one product, the only allylic substituted bromoalkene is shown here. And this one, if we call that A and call this B, these are the same. Same groups are attached to the sp2 carbons in both resonance contributors. Okay, let's look at this a little closer. Here's the allylic carbon, as you note right there. This is a reaction of propene with the bromide radical. It can do two things, as we have seen, depending on where the bromine radical came from. But the bromine radical can do both of these functions. The bromide radical can either add to the double bond or remove an allylic hydrogen. In the presence of NBS, little hydrogen bromide is present to complete the reaction, the addition reaction. So up here, this is as though bromine, the bromine radical came from NBS, and down here is as though bromine came from HBr and peroxide. So either or can occur. Let's look at an example problem. Which allylic radical intermediate is the most stable? Take a look at this, and then we'll look at the answer. So the correct answer is indicated on the slide. And you'll notice that this is a tertiary and allylic radical, tertiary and allylic. This one is secondary and allylic, secondary and allylic, and secondary and allylic. So this one is the most stable among the four that are shown here. Here's another problem. Rank the radicals in order from most stable to least stable. You may remember that the allylic radical, as displayed here, um, is very stable because of delocalization of electrons. This one is primary, secondary, tertiary. So this one's definitely most stable. Then, of course, tertiary, then secondary, then primary. So C is correct. Let's look at some examples of practices with multi-step synthesis. So this is a little bit of a review. Starting with the ether that's shown, how could the aldehyde be prepared? Let's take a look. Now, this is actually forming a carboxylic acid, but we need to look at designing a synthesis and practicing with multi-step synthesis using reactions that we've already studied. We're going to look at 4 examples. This is the first one. And of course here we've got cyclohexyl methyl ether. This is producing a primary alcohol and now undergoing oxidation, forming cyclohexanoic acid. Complete oxidation has occurred of the primary alcohol, making it a carboxylic acid. And just practice in stringing these together to get the product. Now this one, let's say if we had wanted just the aldehyde as indicated on this slide, we would use a different reagent. At this step, we'd use sodium NaOCl and acetic acid at 0 degrees Celsius in the place of this chromic acid will allow us to oxidize it to the aldehyde as opposed to all the way to carboxylic acid. This is the synthesis of 1,3-cyclohexadiene from cyclohexane. A conjugated diene is formed from an alkane, describes this overall process. What are the steps between the reactant and the final product? Here we go, there they are. As you can see, the alkane is brominated in the presence of light. Dehydrohalogenation occurs to form the first double bond. There it is. Cyclohexene undergoes allylic substitution to add bromine. There it is. And the brominated product is then dehydrohalogenated once again, adding the second double bond. So we've used bromination and then dehydrohalogenation twice to make the 2 double bonds in the cyclohexene ring. Okay, here's example 3, the synthesis of 1,2-dibromo-1-methylcyclohexane from methylcyclohexane. Basically, 2 bromines need to be added to the reactant to get the product. There they are. We need to add them. What are the steps between the 2 structures? Here they are on the next slide. We're going to synthesize trans 1,2-dibromo-1-methylcyclohexane from methylcyclohexane. So methylcyclohexane undergoes bromination in the presence of light to give 1-bromo, 1-methylcyclohexane, which undergoes dehydrohalogenation, and then bromine is added across the double bond to yield trans 1,2-dibromo-1-methylcyclohexane. So we've done 3 reactions here. Here's example 4, the synthesis of 3-phenylpropane nitrile from ethylbenzene. Let's consider drawing out a retrosynthesis analysis. But first, before we could even begin to do that, we need to think this synthesis out. What steps are between the above, these 2 molecules, the reactant and the product? What is between the 2? Can you think of it in a backward way? Okay, that's what retrosynthesis is, retrosynthesis. Here's the finish, and this is the start. So it's kind of like starting backwards, but this is 3-phenyl propane nitrile. And just thinking what step removed each time going backwards until we get back to ethylbenzene, the starting material. So here, this is in essence the synthesis of 3-phenyl propane nitrile from ethylbenzene using retrosynthesis analysis. As we will see after we add reagents to the steps, the hydrogen bromide adds anti-Markovnikov as we can see on this slide. So let's turn it around and look at it in this manner. Again, the synthesis of 3-phenyl propane nitrile from ethylbenzene. And this is the actual sequence of steps. Ethylbenzene is brominated in the presence of light to add a bromine on the benzoic carbon. There it is. And then the second step, dehydrohalogenation, occurs with a bulky base, hydroxide. And the hydrogen bromide is added anti-Markovnikov in the presence of peroxide. The nitrile group replaces the bromine, and we have a final product. Now, just a couple of exercises, a couple of problems to look at as we conclude. Which compound will give one product upon radical bromination using NBS, peroxide, and heat? So take a look at this, think about it, and we'll look at the answer. Okay, A is the best answer. Notice it says removal of an allylic hydrogen from compound A forms an allylic radical with 2 identical resonance contributors. And here's the radical that could be formed. Notice it says it will give one product. All these others have substituents that will allow multiple products. But if we take this compound in the presence of NBS, which is a source of bromine, heat and peroxide, which makes the bromine a radical, the bromine radical will remove an allylic hydrogen, which could be here or here, either way is the same, forming an allylic radical, which is what will be the product. And also take a look at this problem, which reaction sequence would give the product in reasonable yield? Taking a look at the various beginning points, you'll notice that we can undergo bromination to begin, and then we can successfully put on OH and this methoxy group in a series of steps. Take a look at that. The correct answer is actually this one right up here, and you can follow that through the best you can. That concludes Lecture 2. Thanks.